Thank you. Earlier this week, I was able to give an update to a little bit smaller group about what's going on with the New Mars project. If anyone here doesn't know, New Mars is the project I'm working on to build a new runtime for Urbit, nominally a replacement for the current var that would have the goal of making knock run as fast as knock reasonably can run, which I think will probably be pretty fast. Also, removing the loom limitations, removing the limitations on the amount of data you can actually store in your Urbit. So for those who haven't yet run into this, the current runtime gives you 2 gigabytes of memory space that's both your persistent memory and your computational space. So the more you're persisting, the less space your computations have to work, and it all has to fit in this 2 gigabyte limit, which currently sort of all lives in RAM and gets snapshotted to disk. So a lot of use cases for Urbit need to push that boundary a little bit, or perhaps a lot. And we'd really like to be able to give people all of the advantages of persistence on Urbit. So on Urbit, you don't write to files. We have a file system. It's called Clay, right? But you don't have to put things in Clay for them to be persistent. On Linux, you have to put stuff in a file if you want it to stick around. In Urbit, it's just your agent state, and it's there for you the next time your agent runs. So we'd like to give all those advantages without this space limitation, and start to try to remove some of the restrictions that make a lot of Urbit applications essentially proxies for, generally we call them sidecars. So my previous project, the WebRTC stuff, didn't really have a data size limitation, it had a compute performance limitation where we're using Urbit to pass setup messages between browsers can establish their own peer-to-peer connection, handle all the video processing, passing tiny little text message blobs around to help the browser set this. Bitcoin node. It turns out the Bitcoin blob doesn't fit into gigs anymore. I'm not sure when that happened. But if you Bitcoin somewhere, and there's 2 Bitcoin full node proxied from Bitcoin app, so that's sort of running alongside the node and talking to it. If you post images in chat right now, you have to set up an S3 button, pass around hyperlinks to the images, which the chat app, and then render image in line. You have to set up with your friends on Urbit right now. So get all of these persistence benefits, all of the developer experience of who worries about persistence? Not me. I put it in my agent state and it's there. And that limitation by building a demand paged persistence. That's a line of work. And briefly, right now, what that looks like, will just be earlier we were thinking hash table of nouns and paging like per entry in the hash table. Work very nicely with how the underlying operating system wants to do paging. So making a memory arena that you'll have the same representation of nouns that you're computing with will live in there, and we will demand page that. Turns out Windows, macOS all handle paging for speeds very, very well. The operating system memory map the whole arena into whatever size file we need, and then let the operating system go get it to actual physical RAM when we need it, effectively transparently. Pages, we will write to them, so what's in RAM no longer matches what's on disk. And we don't want to just write that back. You could state where you some of this back to disk, but all of it now this is the same with Windows 95 if you shut your computer off without running a shutdown process. This is what Windows 95 was doing, was making sure all cached to go to later was actually into disk. Mostly it was that was wait for the orange, it is now safe to turn off your computer thing, and why you hoped that the power didn't go out while you were using it. The embedded database that Urbit uses right now for its event log, LMDB, does most of this already. And so we're sort of borrowing the techniques that it uses, primarily called copy on write. So when you go to write to a region of memory that hasn't been written to since the last snapshot, we'll actually copy it to a new place in the file and then remap that to the same spot in memory. And now you can write to it. We won't and then when we take a snapshot, we'll sync all of these out to disk without overwriting the old file region. So your data is still safe there. And then once we're sure that all of this is persisted to disk, then and only then will we go update the index in the file that says, hey, this region of the file goes to this place in memory. So this is called a copy on write system. This gives us atomic snapshots from our Urbit while not interfering with the operating system's demand paging for reads. So we get another have our cake and eat it too. We get atomic snapshots this way. We also get as big as we can put in on our disks, as big as we can put in 48, 47 bits of virtual memory, which is quite a lot. It's hundreds of terabytes of storage that we can do as long as we have the disk space for it. And the operator will let Linux or Mac OS or Windows take care of paging that into memory because it does a good job of that already. So that's what we're trying to finalize the design for on the Loom location side. On the compute side, one of the first things everyone found out about for new Mars was the sort of 2 stacks compute arena that gives you bump allocation. So when I first pitched new Mars to Philip, the thing that made the idea click was that I'd just been sent to try to make AIMS go faster, and I had been profiling AIMS, and the hotspot wasn't this gate, that core, this loop. It was actually just, the thing that was taking the most time was just slamming a gate, any gate, right? That was, we spent hundreds of microseconds every time we did this, and we went down through 12, 13 deep call tree in some cases. And there's a few reasons for that. One of the big reasons is that you allocate, if it's a gate, you allocate 2 cells to slam a gate. Ver optimizes somewhat for this, but in the general case, that means reference counting. That means quite possibly a malloc call for each cell. So you spend a lot of time managing the memory for cells that you've only allocated to make a function call. This incidentally was one of the complaints of the SKU guys when they said knock allocates for every function call. It's actually a complaint that it's already known in the PL implementation community how to address, and the answer is just don't use malloc to allocate these things, and don't use reference counting for these sorts of things. So the stack allocator, the main advantage that it gives us in that is that it gives you the fastest possible allocation. There's no possible faster memory allocator than just an ALU operation. You're just adding to or subtracting from a pointer, that's it. And we don't actually spend a lot of time managing memory because whatever memory we still need when we pop out of a frame, we copy. It's in general not going to be that much because it's only what you allocated in this time that's still live. And we don't spend any time at all on the garbage, on memory we allocated we no longer need. In contrast to reference counting, where we have to touch all of the garbage. Every time a reference goes to 0, and now it's garbage, now we have to explicitly go and free it. So there's a reason we have reference counting right now, and it means that memory management in the current var is perfectly deterministic. You can, if you run the same NOT computation on the same system same version of var, the expectation is your memory behavior is exactly the same, down, not just down to like when you do memory management, but where the actual allocations for individual objects land. This makes systems programming kind of nice, actually, right? Is that you get repeatable behavior at the systems level, which any systems programmer will tell you is just not something you're allowed to expect as a systems programmer. The stack allocating arena actually preserves this. You're going to make your allocations in the same order if you run the same knock. The pointer is going to get bumped in the same order. You're going to pop the frame in the same order. You're going to copy stuff out in exactly the same predictable memory management, but now it's actually legible all the way up at the knock and hoon. You can say we're going to do a collection here, and we're going to how the result we're returning here is, and how much of it was passed in as to predict a function. We can actually reason about how much copying we're going to do. We can reason about memory management performance completely predictably from within our high-level functional programming language. Just if you're not very far into functional programming, you haven't spent a lot of time on programming languages implementation, I'll line under this and say there's programming languages, it's called memory management, the same thing. It's been for 30 years at least. I think so you're getting closer to 40 years. So why is it easy for me to do this? And it's been taking, well, all of their languages have escape hatches. This is the same as my previous talk. I can do this with knock because we put you in a straitjacket with knock. I want to mutate. No. I'd really like to just make an I/O operation right here. No. Okay, so we built our entire system around these sets of constraints, absolutely, obstinately, without compromise, and now we can solve this problem. So this is another one of those big wins that comes from that same set of constraints. There's the garbage collector. The technology is very similar, but it doesn't run. So garbage collector, if you run in Java, if you run in Haskell, you run in really any modern high-level language, you have a garbage collector. And when it runs is when you fill up your heap. When will that happen? I don't know. You reason through your program to figure out when you're going to fill up your heap. Okay, but I made your heap twice as big now. Now can you do it? So you can't actually reason about when you're going to pay for memory management and how much you're going to pay for memory management. And this is the entire reason given for why we still need to write high-performance applications in things like C or Rust or any of these other systems. Well, if you really want high performance and no pauses, you need to manage your own memory. We're going to get rid of that reason, and you just write your predictable performance applications in Hoon. So the other piece of this, again, I actually touched on more in my previous talk, is the subject knowledge analysis piece, and the part we deal with the fact that Awk is semantically inherently an extremely dynamic language. This, again, is, from some perspectives, it's a good thing. It's one of the straitjackets. You don't get procedure calls. You don't pass closures around. You build a data structure, and then you eval it. But this makes my life hard as a systems programmer, as a language implementer, trying to actually make knock go fast. So I won't rehash the subject knowledge analysis thing here, except to say, put it together with the other things we've just described. We've gotten rid of you having to worry about file I/O. We've gotten rid of you having to try to worry. We've gotten rid of the trade-off between I need to reason about memory management, but I want to write in a high-level language. Here's a high-level language where you can just syntactically reason about memory management. That's what Hoon will be under this system. And subject knowledge analysis on paper is not, maybe it works, it works. The only question here is an engineering question anymore. It's no longer a research question of how do you make not compiled to bytecode look like Java compiled to bytecode, C compiled to bytecode. We're going to do better than JavaScript because JavaScript has to run and see what the actual program behavior is, and then start feeding that information back in to try to make. We're going to do this ahead of time and give you, again, make performance reasoning predictable. It's not, JITs are as bad as garbage collection in this respect. So what's actually done? So analysis exists as a spec. You can go look in the repo. It's a function over nouns, not formulas. So the easiest way to write a spec is in Hoon. So spec in Hoon. It also has some stuff about how jet matching would work, like I talked about before. The stack allocator exists. It runs. There's a tree walking, just sort of naively iterate over the tree. That runs on top of it right now to sort of validate it actually works. It allocates memory. It doesn't lose track of pointers. It doesn't cause seg faults, that sort of thing. And the interface between that, the code generation, and the persistent memory arena is very close to being worked out. Talking with Joe, I was talking with Josh, and he was here earlier this week, talking about when we can. I understand it's frustrating. It's frustrating for me to be single-threaded on this. There's a lot of work to do, and I could see all these wins, but like I could be working on this, or I could be working on this, and someone else could be working on this. So the time is coming and coming soon when I think we'll be able to piece some of this out and say, this is a well-defined chunk that can be built to a spec, especially the persistent arena, getting rid of the loop limit. We'll be able to say, this person can build this, and we'll slot it back in. So we're getting very close. I understand that there's been a lot of excitement around this, matched by a lot of radio silence. And I want to assure you that the radio silence is just because I barely check Urbit during my workday at this point. I just dive in and start cranking through code. But it's getting close. So that's what I have for you guys. If I can go into more detail if anyone has questions. I don't know how much time we have before that hard stop stuff. Okay. Logan.
What are the so I understand the desire to reserve a few bits for various flags and other things, but 16 seems a little large. Is there a reason why you'd be aiming at 48?
That's actually a modern CPU MMUs. So your processor word size is 64 bits. Your MMU only handles 48. So if you're running on x86 64, there's been talk among Intel, AMD, everybody forever about maybe we'll build some that give you 57. Mm-hmm. Nobody's actually done it yet. So okay. Even the very latest Intel CPUs, their MMU only actually handles 48 bits, and then what they do is give half of that to the kernel. So you actually get 47 bits of user space virtual memory in most settings. Mm-hmm. So which is hundreds of terabytes. You can actually feasibly think of applications where this would be a straitjacket, but it's for most use cases, it's not going to be a straitjacket for a long time.
Sure, no, I agree. Yeah. I was just curious as to the number and rationale.
Yeah, no, it comes from
sure.
Complain to Intel.
Yeah, literally.
I will too.
Sure, thank you.
Anybody else? Just to go a little bit more, we actually don't use any of those bits for tags right now. The bits we use for tags are actually, it winds up being the higher 3 of the pointer, but that's because we shift and get rid of the lower 3 zeros because we're 64-bit, 8-byte aligned, so there's 3 bits at the bottom that are always 0. So that's actually, we have 3 tag bits that aren't in those 16 bits at all. Christian?
In an extremely high-level, non-technical sense, what use cases does this unlock within, say, 12 months to 2 years?
Quite a few. The very first exciting thing is that I actually think the big win of Urbit is developer experience, and the big hole in the Urbit developer experience right now is the necessity of sidecars. And just getting rid, or mostly rid of that necessity, I see as a big win. People are going to use Urbit because of the apps that will be on Urbit, and apps will be on Urbit because developers will want to build on Urbit. So, and so I completely agree with the foundation's push, like push on Urbit DevX, but I think this is one of the biggest friction points in Urbit DevX right now. The fact that we have to use, that every user has to have an S3 bucket set up for them to post images in chat is a limitation that hurts, right? And if we, getting rid of that is, on the performance side, it really just, so like, Ames is CPU bound right now. And like, so what could you do with a megabit as opposed to 100, or 10 megabits, or let's just say, what could you do if you could actually max out your NIC with Urbit? A lot of that too will come from the remote scry stuff where you don't have to do an event log hit for every packet. But what can't you build on Urbit? Everything that we have on the Tacen side right now, all the things that we want to put in sidecars right now, that we've built but put in sidecars, or that we haven't built because making a sidecar is too awkward, is unlocked by this, I think. I want to build video calling on Urbit. Like, I actually want, like, I have a connection to this person already. I don't want to deal with setting up another one.